Okay.
Restart. Where shall we start? Do you want to ask some question or?
Yeah, I think we'll start there just with some questions.
Yeah, go on.
So I've started taking notes on the 3 governing equations.
Yeah. Governing equation. Yeah.
And there were a few. If I were to like write them up and send them to you or something, would you be able to help me answer them?
You can. In that case, can I share your screen? Like, if you can show me any, or you can also send me a. Is your letter in the PDF form or is a
letter?
Your note is your note in the PDF form.
Oh, my notes are written on paper.
Written on paper.
Yeah,
so
I wrote
in
them.
That case, how
but
can I send you
I can send you the document that I'm taking notes from.
Yeah, you can either take a picture of your note or you can. How do we?
So this is Can I send it through the Skype? Does that?
Yeah, you can use Skype. Can you just let me know? Can we just talk? What type of the question? Do you understand the equation now, or do you have trouble with this notation?
I think the notation is okay. There's just lots of like maths principles that I haven't used yet.
Can you read? Can you read from your side?
Yeah.
Such
you have to apply Gauss's divergence theorem.
Yeah, the divergence.
A surface integral to a volume integral.
That's correct. Yeah, that's right. You just if you go to the divergence here, so you have this notation of any field says F, then you should be able to convert into the volume. So basically the surface. Yeah. This volume. Or you send me something. I have a look. So that is something says phi and the volume. Okay, I'll see what you have done. I'll just check. Just check what you have sent to me.
So is phi the same as nabla F?
Let's just check. We just download you. Can we download that? Okay, open it. Oh yes, I think. I tried to open your PDF file.
Yeah, you should just press accept and then.
Yes, I accepted, but couldn't open it. Can we download that or is it still download at the moment?
Yeah, it's downloading.
Yes. So what you're trying to do? You're trying to work out the You see, the equation have several forms. They have the very compact form, which use use the Pearl, use delta. You got the Laplacian, and that is in vector form. Alternatively, you have his components form. So if you can write this down, you can expand that delta into the partial differential note. Okay, I can open it now. I just okay. I can open that file. Have a look what your question is.
So this is just a document that I was taking notes from.
Yeah. Okay. So that is all. Oh, this is a PDF. That is a lecture note, right? That is a.
Yeah.
Okay, where's your question? Which page?
So if you go to page, I'll just open it up on mine. One second, sorry.
Which page?
I'm just trying to find it. Sorry, I'm just trying to get it.
Take your time. So basically, we are dealing with vector and scalars, which have they have 4 variables. Okay, they got 3 for the space and 1 for time. So therefore, you are dealing with multiple variable functions. So in that case,
I found the page.
Yeah. Okay.
Page 9.
Okay, page 9. Okay, go back. Page 9. Yeah. Can you see my side?
Yeah.
Yeah. Page 16. Oh, it's not from. It didn't come from the. It didn't come from the. This is a book page. So what's your page? Oh, that's 15. We start from 15. So
Oh,
which section?
maybe.
Which chapter? Which chapter do you?
I'm just looking at chapter 2, the same chapter as that one.
Okay, let's just go to. Okay, this page number show up. Okay, I just give you
23.
page 8. Yeah, 23.
Yeah.
Page 23. This is 6 now. It's oh, there's 1, 10, 12, 23. Where are they? I just type here. Can I just type 23 here? 23. Let's go. Yep, this 23. Is this your page?
Can you see equation? Oh no. I think if you want to type it, you type 9.
Type number 9.
Type 9.
Yeah. Oh, it's not 23. Number 9. Okay. Number 9 and enter. Is this one? Can you see my side? 23. Yes, it's 23. Page 23.
Yes. Yes.
Okay. So which question?
So equation 2.12.
2.12. Yeah, that's right. That is a notation for the volume. That is volume,
because
right?
what they did, I don't know how they went from 2.11 to 2.12. They just said that they applied.
That is use the divergency. So because it's a divergency, so the this is so basically here. Because on this side is this is capital D. Capital D, that is just for partial. Is the short for the four partials derivative, right? And
that's the total derivative, I think.
The total derivative, yeah, that including time. So what is happening is they just introduce. See, so far they just use. So here they use Gauss. So this one. So this is a surface. See, this is just the integral. For the enclosed. When you see the circle here, it just means the surface. The area is enclosed, right? Yeah. So therefore, if I draw I should use my side. If I draw this one, I can't explain. So basically, you got irregular surface here, right? So you are supposed to finish that integration. Say this is a dx, this dx, right? And dx has a proper position. It's called n, normal position. In the meantime,
what's n? Is n perpendicular to the surface?
To this, yeah, that is a directional. That's direction unit. So see. On the other hand, you got any vectors. So in this case, what do we call it? It's called F. It's called V. That's velocity, right? Yeah. So basically, what's happening here? What's happening here? So you got so this is just one of them. So this is just one of them. So this is vector velocity, and this n. I just enlarge that this n should be proportional to give the direction of this particular small areas. You can call the dx, dy, or dz, depending on the direction. So basically, that is ds give you that area which have proper direction. So in other words, this one you see is this one. I just copy that one, so that this is one. This is called the flux. Have you started? Do you remember when you started the Faraday's induction law? Yeah. We're talking about the flux. The flux is the integration of the B, okay, dot product. So this is exactly the same thing. Can you see? So you can call this is a flux. You can call this a flux.
Oh, okay.
You see? So you can call this flux. So, but what happens is that you have to do this. You have to, in order to do that, you have to get this separate into very depend on the coordinate you use, right? I drew some of them. So you have to finish everything here. You have to go through everything. So the n is here. So different. You have actually you finish the wall. That is a guidance. You see, you are short. We are studying the very compact notation to represent a partial differential equation. Okay. Now what Gaussian law says is exactly the same. What Gaussian law says that you actually you don't have to do this surface integration. You can simply just to convert into consider this kind as if there's any source inside, of this vector field. See, so you end up with instead of doing this tedious this function, Gauss says, well, if you know the divergence, okay. If you do this vector, so that's the shorthand. See, that's for this partial. This is just a partial derivative, right?
Yeah.
If you know this one, the question becomes simply say at this time I will use because they use velocity. I just probably use I have to use v, but this v is different. Okay, so this v refer to volume. This v to the volume, or if you want to write more, you can dx. So you can rewrite this. This is dv, so there's a volume, so that is dv. Can you see? That's dv.
Yeah.
So instead, say what to say, if I just draw the 2D diagram, so instead of do this integration, you say from here at every point of surface, then you can actually integrate, according to the density distribution, you can do the volume distribution inside this space.
Okay. Yeah.
That would be equivalent. That would be equivalent to that.
Okay. Right. I understand.
If you that's right. I give you one more example. For example, if you do you know the Coulomb's law? Coulomb's law. So there's a Coulomb's law that the force were equal to, say, if I use this one, is 4 pi epsilon. That is that's constant. You usually write it to k, right?
Yeah.
So that is a q. Oh, sorry, the field generated by the point charge can be written as this case. Okay. Yeah. So what does this mean? This is exactly the Gaussian law. Why? Because this is, you can rewrite this definition into Gauss law. What can you do? Can you see the 4 pi r square? So if you have 4 pi r, if you time 4 pi r square on both sides, right? And the other side will simply became the what you call the density. This is a q. There's no q. There's just one q. Sorry, only one q here. So that will just became epsilon. And the Q, okay, the charge. See? Yeah. So this actually is a special case. You have a spherical, because it's just talking about spherical, because 4 pi r square exactly is the area. Okay.
Yeah, it is.
So this area exactly can be written as into this form. You see? Can you see the similarity here?
Whoa. Okay.
Can you see that? Can you see that? So that is you see. I have to give you some idea of before we go further. So this is a preparation. If you're interested, you can have to look. So basically, in physics, mainly they are just limited, finite number of partial equations, apart from Einstein's general relativity, which I don't want to touch because that is a purely mathematical geometry. See, but apart from general relativity, these are finite number of partial equations. Can you see? First one is wave equation. Can you see Laplacian? Can you see that sign?
Yeah, I can see it.
So right, and also basically in physics we're dealing with a variable which is a space, and time. Yeah. Okay, so that why not surprisingly we will got is a partial notation here, and x and y. See, that is by nature this is its components when you see a differential equation. But this equation in physics are limited. See, this wave equation can be described any wave, like a sound wave, water wave, light, electromagnetism. Okay. And the second one, we just go to that one gradually. So you can see this again. You see the partial. This is called the diffusion equation, which can be described if there's a say the heat transfer. Or even if you put the coffee, if you put the coffee, you put into the colors into the water, so that will diffuse. That's due to density gradient. That's due to density, different from the issue you are studying. You are studying the pressure driven, right? Pressure influenced. Yeah. And then in a special case, go to Laplace equation, right? This is a this also Poisson equation also is a general case of this case. Can you always see this? You always see this term here, right? And even you go to the quantum mechanics. If you want to start quantum mechanics, you can see you choose this Laplacian sign here again. Can you see? But of course, in this case, u is not velocity. U is actually called the wave function. So when you start quantum, that's a wave function.
Okay.
Yes, that's Schrödinger equation. Then we go to the Navier-Stokes equations here, right? Again, it's in the compact form. The difference is only difference is that they got this. You have introduced more this partial derivative notation. See, it's called what we call the curve. We call it so the delta. You can call the delta. You can curve. Doesn't matter. And so that we will return to this question, okay? But I will also take this chance to tell you that when you start the high level electromagnetism, you can simplify everything in electromagnetism into 4 equations called the Maxwell equations. Can you see?
Oh, okay.
It's all end up with density, you see, because we're dealing with 2 types of field: vector field, electrical field, and magnetic field. See. So for the Gauss, this Gauss law again, can you see? You can. The first question just divergence law. See, because this is in law here is the charge density. So this is different from the density we just called the mass. It's different, okay? But it is a charge per volume. It's per volume. So you can imagine that if you do the volume integration in here on this side, then you got a delta volume here. What you get? You get a Q. Can you see?
Oh, okay. I see that.
Here? That's a return to our discussing now. You see, but just let you know, this notation, this is common. Every equation, every partial equation in physics involves this notation. So not a surprise. Don't get a surprise. So let's return to the equation we are interested in. This one. Okay. So basically, this is in what we call the compact form, based on this notation. Okay, so shall we return to your PDF? Where's your PDF? Check your PDF here. Okay, any other question?
No, I think that made sense. That was good.
Okay. Another, have you said this is a divergency or Gaussian's theorem? Do you know another one which confirms the surface equation into line integral?
Oh, I haven't seen that one. No.
I haven't seen that. I will remind you that if you're interested, if you want to know more about that, I just return to the note I have here. So if I follow my note here, so that is a part. This is a complete picture of the. So actually, we are starting vector field analysis, right? So that is the divergence. That is just one of them. Divergence curl is another thing. Curl is referred to the in your case that's referred to the local spin, or they call it eddies, right? Or they call to you actually or vortex. You call the vortex. So basically, you got this diagram here. This is diagram here. So divergence just refer 2 types of things. One is called source. Can you see the positive charge in this example, right?
Yeah.
This is negative charge. You see, it's just acting as a sink. If this is just a sink, in the positive one just act as a source. Okay. In your case, in your simple model, you are not involved in that, right? So therefore, in your case, that divergence is always 0, right?
Yep.
Because in your case, we return. So this is your model. Can you see? This is your model. So this one.
Which one?
See? So you got this one. Can you see my writing?
Yeah, I can see it.
Yeah, so this is your model. So you got inlet here. So you were just. What happens is that if the velocity, if its viscosity is snow, and also the velocity is snow, and you got a streamline, you got a stream, or cause have you heard the laminar stream? Nonlinear
Yes.
stream is called smooth. You see, that is that is the goal for design the airplane from the how to say racing car,
Okay.
high speed train, because in that case they're trying to minimize the turbulence, right?
Yeah.
Because the formation of turbulence will always increase the pressure, the resistance pressure. Again, if you, I think we're after you answer your question, I will go to some critical point on your modeling. Okay, but
Okay.
here I just see this graph. See, in general, the curve actually you can use the graph is actually, can you see this co-centered circle here? Can you see that?
Yeah, I can see that.
That is a typical feature of the magnetic field. For
Oh.
there's no source. Can you see? There's no source inside. So, and in other words, the field, if you draw this vector field, then they must finish the circle. Okay, they must finish the circle.
Okay.
So that's why, if you do remember when you study the current, if there's a conductor current here, right? So the magnetic field always circled around it. Can you see
Yeah.
that?
Yeah, I
So
can see that.
that is this such called a local spin, by you just abstract the vectors can be described by using curve. So this is very important. Curve is described the formation of the vortex, or you can call it chaos sometimes. So basically, that is, can you see this local? This is a turbulence. Can you see a turbulence here?
Yes.
So
Yes.
therefore, then by the time we're talking about your model, then we will discuss whether your model allowed you to actually by play with parameter, can to achieve a certain amount of the certain degree of turbulence.
Yeah,
That's
I
that's
can get
that's
turbulence in this. Yeah.
that's good. That's another issue. Okay, then just return to your PhD PDF. Any question on this note?
No, that makes sense.
Do you have any question on this note?
No, I think that was good. I understand.
You understand now? Okay, good, good.
So I was just actually I did have one question.
Yeah.
Am I able to like use these equations? Can I like can I get an answer or something? Is that possible with these? Or is this just theoretical?
I think the bottom line, I think this is a general equation. You see, if I return to my note here, I will give you some answers here. This is general note here. So basically, I don't know how far you have gone. So basically, you have to understand a lot of things before we can answer your question that's more specific. So basically, where are we going? We go to the lesson one. Okay, appropriate lesson one. Now here is one of the form of the basic equation, like here.
Yeah, I can see that.
Okay, now in this, do you have trouble to understand each term?
Not really. I don't think. So the first one.
How about, for example, do you know? Just ask a question. Why they call this as you have negative that draws P for pressure? Why we call this is force per volume?
Why is that force per volume?
Yeah, why? How can you prove that? Do you know how to prove that? Or do you want to know how
No,
to prove
not yet.
that? Yeah.
Yeah.
So that is something we can learn if you so basically, if you, for example, if you want to know this formula, because each term, these are various terms here. Another term is the most difficult term is this one. So this viscosity, this is the square term, the Laplacian. Okay, this velocity.
Yeah.
Do you know how to interpret this term?
No, not really.
Well, basically they assume that you have if you want to know, we can spend some time on it. Otherwise, we just let you know that this different term represent different force intensity. So this force per volume. Okay.
Okay.
So this actually is nothing but Newton's second law. So Newton's second law says is m and times the first derivative. So that is velocity.
Yeah.
Were equal to the sum of all forces involved.
Yeah.
Okay. So relatively speaking, this force is external relative to a tiny, very small q. So this q depends on how you choose your x and y, z. So if you choose this way, so there will be x, there will be y, there will be z, right? So in that case, so that this side will be dx, and there will be dy. Okay, so it is dz, there will be dy. So basically, so that is this is a starting point to derive this equation, right?
Yeah. Okay.
So if you're interested, we can just you say if you divide them by volume. So you divide it. So if you divide this, if just m divided by volume, we know it's great density, right? That's how the density appear here.
Okay.
So that's still the first derivative of velocity.
Yeah.
Okay. Since that way, then that what they do is just rewrite as the lowercase f. Okay. So this f, where this f, so this f will represent the force. So this is the total force.
Yes.
Divided by the volume. So therefore, you got this density here, and then use the differential, because in this case you have to bear in mind. So the velocity in this case, because the body is moving, so this is in general is a function of x, y, and z and t, right?
Yeah.
So therefore, you got if you just do the so basically when you do if you do the total, this is a total differentiation, right?
Yeah.
Then you got the sum, you got the velocity first to the time with time, right? Then that have, because x, y, z, the x, y, z are function of time too. So x are x time, y also the y as function of time.
Yeah.
And that is function of time. Therefore, so you have to use how the chain rule. You know the chain rule. You have to use the chain. You basically use u. You guess use u. That's velocity. You have time you time x, and you use x. You x time so this is use ux. So you have to you time t, right?
Yeah.
So you just do you know that? Can you do that, or do you want to? Because this is somewhere you can show in your writing that you know how to obtain the equation.
Yeah, yeah.
And also,
I've done this proof.
you
I
have
think,
done that.
before.
Yeah. So you know how to do that. So that will eventually give you the left hand side. We give you left hand side of the equation.
Yeah. Okay. Yeah, I can see that.
Yeah. So you can you see that? So that here we got the velocity. Sometimes they use v, sometimes they use u, but just they just denote that as the components u, v, w, right? So basically, you got the x component, they got y component, and the k component here. So a z component. So that is 3. That's why when you see the what I say, when you see the component form, you will see this case.
Okay.
But in our case, this is what we call, normally we just assume the external force is equal to 0. Why?
Okay.
Because in your case, you are studying the almost horizontal pipe, right?
Yeah.
So in that case, that the gravity doesn't control, is not irrelevant.
Oh, yeah. Okay. Yeah.
So that's why in your equation you only you pay attention to this first 2 force, right? That's pressurized. The second one is more complicated than the first one. So basically, let me see if you want to know more. So basically, the same equation, the various equation can be written into different form. Let's go to my note here. So where's my note? I just reduce that a little bit to see. Where are we? I have to deduce that. But let me check what we're going to. This way. This is something I want to show you here. So you have to understand that.
Whoa.
Okay, let's go to this
Yeah,
part. Okay.
yeah. How do I solve the? Yeah.
It's not you don't solve it now. It's hard. There's no analytical solution.
Okay.
There's no analytical solution. But you have to understand this Navier-Stokes equation have different form. Okay, this is something you have to understand. First is in the more compact form. Is more in compact form. Can you see? So this form we've used in a textbook. But if you really understand, so that is compact form here.
Yeah, that's what I've seen before. Yeah.
Another thing you have to you have used discrete form,
Mm.
where you can actually apply this equation to different, the given time interval. In this case, time will be the fixed. Delta t will be fixed.
Okay.
And so the reason is that the computer cannot solve differential equation. Computer can only solve difference equation. Do you know difference equation?
Yeah, okay.
Hello. Hello. 哦，不在。你打开手机好吧？你好，谢谢，好，再见，好。So where are we? So basically, if you're interested, we can also go to some detail of how to use difference equation to solve this different equation. Okay, and another form is what we call the component form. Can you see here?
Oh, yep, I can see that.
The component form we're just without use the delta sign, we just write down this notation here. Okay.
Okay.
So in this case, this is a case that where if you say I, and that automatically means that I will equal to x, y, z, and t. That is that's the short notation here, right?
Yeah.
And so when and another thing, when you see this what we call the component form, they also have a shorthand. This is a common. So whenever you see for example, if you have say let's go to example. Let's go to the form of that viscosity, right? In your case, you have to pay attention to the viscosity. So this one, let's just show you how to. This is not so. Here is good example. Let me see. So. Let's go to the viscosity. Where are we? Where is viscosity? So let's go to the other side. Not here. I just go to another place. Okay, this is something I want to remind you. If you want to know the component form, you have to know this convention that. Okay, that is a. Can you see here? Can you see my pen here?
Yes, I can. Oh, your pen. Yes.
Yeah, can you see here? So basically, you have to again, even in written into components form, they have the assumption you understand this notation. Why?
Right.
If you say that if you say 2i, actually they refer to the sum. You can see.
Oh,
They
they're
don't.
referring to the sum.
They don't write the sigma anymore. But this term will contain n terms, right? Do you understand?
Yeah. Okay.
So that's also this convention people used when you write a component form.
Oh.
And so that is, again, this is component form of this equation here, right? So that is from here you can see, roughly speaking, this is viscosity form. Can you see that? Do you remember that viscosity form that uses Laplacians, right? Velocity here.
Yeah.
So
V.
this is square, or you just use this upside down triangle. This one. It's the same thing. The same thing. So basically, this involves the second. When you see this, the sign, they will involve the second derivative, right?
Yeah.
So why is the second derivative? Because you can see the viscosity is due to the shearing force.
Yeah.
So basically, due to shearing force arising from the gradients of velocity. Can you see this notation here?
Yes.
Can you see this notation here? So basically, you just pay attention here. This says this is a u and v. It could be u and v. So that's sometimes we say u. This is u. That's x, right? If you just take two of them, so y. So that gradient. So this is gradients. We use the first derivative to represent the gradients. See, that is the origin of the viscosity.
Okay. Yeah.
Okay, but after I prepared this note, I realized there also have some series defect of this general equation. Do you know why?
Oh, really?
Because mathematically speaking, this formula can go as small as possible, but this doesn't make sense because this is a real molecule which make up this blood or flour or any material. Do you agree?
Oh, yes.
So friction or these tensors, they use tensor to describe these frictions or shearing force. It's actually macroscopic. It's not microscopic. It's macroscopic. So your modeling have some series defect.
Oh, okay.
Because just ask your question. No matter how small they choose this volume, right? They still use this formula. They still use formula. So basically, but this doesn't make sense because if you go small enough, what you will get is an intermolecular force. Are you doing chemistry?
Yeah, I am.
You see, that is a force can be formulated. You see, this is molecule 1, molecule 2, right? So that force, if you just write down here.
Yeah.
So intermolecular force can be described. You see, you don't have to assume anything. So that is intermolecular force. Can Ij, right? So you have two molecules here, I and J, right? So in general, this force will have this form. Do you remember? So you got attraction here. So they got attraction here. They got repulsing if the distance getting very, very close. This is R.
Oh, okay. Yeah, I have seen that. Yeah.
So that's why, apart from this traditional way to solve the problem, they have another it's called molecular dynamics model, MD.
Okay. Yeah.
So that's why I actually, when I read this, when I prepare this note, I realized that you don't have to, there are many. You can make some critical discussion about this general equation.
I can do that.
Some with their, with their assumption, they assume that you can still use this the force formulas to describe the intermolecular interaction. It is basically it is assumption, right? It is assumption, but you have to bear in mind that molecular dynamics modeling is more realistic. I wouldn't say more
more realistic.
Realistic. Okay. Now they have some. I also have taken this opportunity to give you some critical comment of your modeling here, right? I understand it. I understand now. I understand now. What you're doing is actually by changing this the cross section, right? Okay, and then by using modeling, you actually can calculate if you just use x, this is x, can you see the x direction, right?
I see x.
So basically, you actually you can call it A here. That is say the B here, or can we put more A B C? So it's A B C. So sorry, A B C D, A B C D E. So basically, you can calculate the pressure. You see, the result you give me last time is that the pressure at this position is pressure. Is this can we say if you just use this?
It's a pressure at A.
Pressure A, right? Okay, but is your model allowed you to calculate the pressure downstream?
I can calculate it anywhere.
Yes, good. Try it, because why? In your case, this is what we call the pressure drop. Can you see delta P here? See?
Yeah.
So basically, you have to consider the single pressure at the inlet is insignificant, is not important. Because in your as your daddy said, in your case that the blood have resistance. You see. The blood flow have resistance. So you have to go back to the question itself. So basically, if there's no narrowing, see, so the blood can just go very smoothly, right? The blood can go very smoothly, go through that one. So what happens, because there's narration here, right? They not just increase. When you say, oh, they just simply the velocity increase here and it became slow, it kept the same, return again, which is not the case. Because what happened? What really happened? I realize now is that this is similar to so this phenomenon is similar to the resistance, like the CT circuit. Do you understand? Can we just draw a CT circuit here, right?
Yeah.
So what happens? If you put a resistor here, right?
Yeah.
The current is the same. The current is the same. The current is the same. But you have to maintain this current, the same current here, you have to create the pressure, the potential difference.
You have to have bigger potential difference.
Higher, got higher. See, so you get higher, you go to the potential drops because of resistance, right?
Yeah.
Then when after finish, then they go back again. So basically, you need to pay attention to this one. So this one. They must create, in this case, the potential difference, V, right? Of course, we just use V in Ohm's law. That is the current, electrical current, will equal to the difference, the potential difference, and divided by R. Now, in your case, many people have done, some people have done it. Is actually the problem can also just introduce resistors here. You see, this called resistance. That's due to the narrowing.
Yeah. Oh, okay.
So
I can
basically,
see that.
so you can what you if you can use I, or some people use Q here. Q represents the flow rate. Okay, the flow rate, not the velocity. Okay, so this red line, this red line is the velocity. Okay, this is velocity of individual parcels. Okay, individual parcel. Then flow rate, the flow rate by definition, the flow rate is how much quantity, how much mass, how much blood,
With respect
how
to
much
time.
blood goes through the cross section. Okay, so this is the same. So the current also, electrical current also defined in the same way. That is just I don't want to confuse. This is Q for charge. You see? Can you see?
Yeah.
In the Ohm's law, they counting how many charge to go through that, right? Due to resistance, the pressure drop. So this diagram, actually to cut the story short, this diagram you should pay attention. So you have to not just calculate the first the inlet, you have to calculate this trend line here. Because can you see each in analogy with of the resistors, so each time you pass through the resistors, the pressure, you have to create the difference. Otherwise, the flow cannot move.
Oh,
because if you simply use the Bernoulli equation here, you get nothing new, nothing important. If you use Bernoulli equation, so this P, so use the Bernoulli equation. This is Bernoulli equation. So this E, so pressure E must identical to this one. So Bernoulli equation gives this nonsense. That nonsense is useless information. Can you see?
Yeah.
Because Bernoulli equation is just to tell you that, well, you have to maintain that another concept. Since yours, did you notice your flow, the blood, you have to check the assumption is incompressible.
I think it is incompressible. Yeah, it is. It has to be.
It is compressible. Then you have to the issues that whether that is something we can discuss further, but not.
But I think I was going to make the assumption that blood is incompressible.
Yes, but if you make such assumptions, right, then you have to that you can simplify something, but then you have how to say. But we'll talk about that issue next time. But here we have to draw your attention today is that you don't just use the Bernoulli equation to get this useless information, right? You have to really see. You really have to. So basically, you have to answer the question that you can talk with your dad. Your daddy. So basically, he described that the post-narrowing not happen not just one place. Okay. Sometimes post-narrowing at several places. So should this happen? And this is so basically you can argue that this is equivalent. This should be equivalent to the resistors. Okay. It's this kind of the resistors in series, right?
Yeah. Oh, I can see that.
So therefore, the pressure, if you use a different color, the pressure should continue this drop. Okay. So the pressure will. So if you just go to this the electric potential, right? Every time you pass through the resistor, it drop a little bit. Okay.
Yeah.
And you drop a little bit. You drop a little bit, right? Okay. That's a trouble. You see, because for the normal people who have no problem, who have this problem, their flow rate must maintain at constant. Do you agree?
Yeah, it should.
So that they have opportunity to to pick up carbon dioxide or to release oxygen, right? If this your pump here, this is your heart here, this is your heart. Your heart is just like a piston, right?
Yeah.
You push here, but if the resistance increase, then you have to push it harder to maintain this pressure. So there's pressure difference. That is the problem. That is a medical issue.
Yeah, that's the problem. Yeah.
That's the problem. Is instead of just calculate the single point, at the inlet. Do you agree?
Yeah, I agree.
So that's my recommendation for your modeling. And another thing you can do is actually you can change the geometry. You can simplify. So let's just change the color to original. So that's my recommendation is apart from this simple geometry, right? You probably can just define this area that is more complex. So if it's off center, you can use off center, or the product build the tube inside. See?
Oh.
So you can see if you can build, because nobody know what's going on, because those you say they can grow up something, right? And they not just perfect. They can be more complicated than this one.
Yeah.
In this way, I'm sure, just from common sense, that the resistor will increase, will change. You see, so it should change. Okay, so that's probably more important to model to see due to this geometry complexity, right? Or you can
look at the pressure gradient.
Or pressure drop. For example, you just open this kind of the gap here to let blood go, this cross section, right?
Yeah.
And to see because ultimately you are interested in the drop in the pressure.
Yeah, that's okay.
Because the body want to maintain the blood pressure in order to maintain the flow rate. Okay, so therefore that's why they had all kind of the heart disease, because the heart can pump extremely powerful, that will damage a lot of things. Okay, you damage a lot of components of the heart, or you actually cannot sustain. So that is all the origin of this medical problem, I think.
Okay.
So trying to manipulate the geometrical parameter to see if you can get some different value of the pressure drop.
Yeah, okay.
Okay. Any other questions? It's up to you. We can if you want to go to writing part, we can certainly have to explore the some detail of these equations. And because that, as I say, that involve depending how much time you want to spend on that, you have to give you outline here. So basically, you have to familiar with different form of the equation, right? And then you, in particular, you have to get entrance how computer enters, right? So how to teach computer, or how to write the formula.
Yes, okay.
To solve this problem. Then you can make an evaluation. Another thing I want to add is that you probably have the research question seems a little bit over general. Perhaps you can say to what extent can the pressure to the flow rate would be really influenced by geometrical features of the of blocking. Okay, so instead of arguing the whole validity of, but again, this is just my personal opinion. I think this is this approach can generate a beautiful seems realistic patterns.
Yeah,
but they must ask something essential. Okay, can we rely on this?
Yeah.
Simulation?
So did I send you my?
You don't. Yeah. Go on.
Did I send you my new question? I changed my research question from the last one. I got a new one.
Yeah, go on.
And I think it's a lot more
specific. You must be more specific. Instead of question the whole idea of you to based on this is where the CFD is based. You just arguing that can we say to what extent that the ratio the pressure drop to the flow ratio obtained from this CDF modeling can be realistically described the medical clinical observation. That pose your data can help you. You understand? Because you get me something. Okay, you send me something. Okay, to what extent can computational version model blood for blood flows through the stored water arterial vertical so can provide accurate means of assessing the severity? Yes, but it sounds a little bit. If my remark on this is that you have to. Let's give me, that matter. Give me probably I will give you feedback say tomorrow or Monday. Okay.
Oh, okay.
To see, I want to. My first impression is that is too medical oriented statement.
Yeah, I think that was the problem.
Rather than physics, okay, or mathematics. So I understand. I understand trying to mean, but my understanding is that perhaps you will see that to mention is that whether this simulation, I mean the CFD simulation, can provide the guideline. To what extent can we just recall to what extent can rely on this provided provide reliable ratio of the pressure drops to the flow rate or velocity, right? What's the parameter? Just the flow rate, okay? Because that's more modeling specific, right?
Yeah, it is.
I think there must be the gap. That's why I suggest at a certain stage we must use some direct measurement from the say MRI, and to get some value which is more realistic.
Yeah,
but
we can do that.
but keep use your model, okay? Keep use that software to see if you by change the more complicated channels or the tunnels, right? Tunnels, then you should be able to get more variety of the pressure drop.
Okay.
So essentially, you vary you treat that the geometric structure of this narrowing part will actually make the resistance increase. Therefore, the heart must pumping harder than usual.
Yeah.
And that will be the origin of the heart disease. You see.
Okay. Yes, that makes sense. I understand. Yeah.
So what you can do for this weakness, so you can continue to prepare the question, and I can from my side will pick up something I think is useful for your writing.
Yeah. One thing that I wanted to start.
Go on. Hello. Soft line. Hello.